Hello and welcome back to week 6 of Project PhoboCam. Before we prepare our samples of simulated Phobos regolith by putting them into the desiccator, it's important to understand their atomic structure before desiccation and how it will change after going through the desiccator. And the way we do this is by blasting them with X-rays in the process of X-ray diffraction. This diagram shows a schematic representation of the underlying what's called smectite crystal structure for our clays before desiccation. You can see that, roughly speaking, they consist of a number of layers with interlayer water between them. But when we desiccate them and we remove that water, it creates an empty space between these layers. They can then collapse onto each other in a process called interlayer collapse. This leaves the crystal structure roughly the same in the X and Y directions, but completely altered in the Z direction by reducing the spacing. To test this hypothesis, we illuminate the crystal before and after with X-rays that then scatter off at a number of different angles, and we can use this to build up a map of how the X-ray intensity varies as a function of spacing. Roughly speaking, what we expect to see is 3 prominent peaks both before and after desiccation, but the peak corresponding to the Z direction will shift to smaller spacing when the interlayer collapse takes place, whilst the other 2, roughly representing the X and Y directions, should stay the same. So, let's put our samples in. I've selected one of the montmorillonite samples and one of the non-tronite samples. We then put them into an X-ray diffraction machine, which is a pan-analytical Expert Pro multi-purpose diffractometer. This device will illuminate the samples with X-ray radiation from copper atoms with a wavelength of around 1.54 angstroms. So while the pre-desiccated samples are in the XRD machine being measured, it's time to prepare for the desiccator to be fully operational. Here is the last thing we need. We have 2 nitrogen cylinders, each one weighing about 85 kilograms, and the idea is that we're going to hook these nitrogen cylinders up using this cable to this regulator. The nitrogen tube will come out here, it will go up over this cabinet over here, trail along the roof here, because the room through that wall is the room where the desiccator is. So the idea is that if we can drill a hole through this bit of plasterboard here, we can then feed in the tube directly into the lab and into the back of the desiccator. So let's get started. Here we have a drill. Let's check that it works. Fantastic. So let's go make our hole then. Get it lined up just about right. Okay, here we go. Okay, now I'm just going to install the pipe, get it through the hole. Okay, that should now be able to just be poured through into the lab. Right, so the pipe has now been attached to the desiccator. Oh, and what do you see, I've put a little health and safety message on the desiccator. Now, we had a little bit of an issue because the red pipe I'm using is 8mm in diameter, and I need a 6mm one to go into the airflow tube. So, well, we had to do a little bit of a bodge job just with some adhesive and some tape because we need to start the desiccator today. But anyhow, that's fine. And attached here we have a valve. When it is perpendicular to the direction of the pipe, no air will flow through it, and when we rotate it like this, this will then allow the nitrogen from the cylinder in the other room, as you can see the cable stretching out there, to flow through it. So now what we're going to do for our first test run of the desiccator, I'm just setting up the data logger now, getting it running on the computer, because I want to check that when we let nitrogen go into the desiccator, that we expect to see the humidity dropping over time. So we pump out the air inside of here and replace it with dry nitrogen. So I'm just going to go outside now and turn on the cylinder and see what happens. 1 nitrogen cylinder now running. Houston, we have a problem. It seems that just when the desiccator was working, we were getting the nitrogen going in, everything was going according to plan, and we were getting the first data appearing on the computer. Two of the wires seem to have crossed on one of the sensors, linking up the ground with the power in, and it has effectively fried the data logger, which is no longer working. But not to worry, because we looked up on the Argos catalogue and found a portable weather station that will do everything for us and even wirelessly transmit it all to your phone. So now I'm going to cycle halfway across Oxford in the middle of the night in order to go get this new weather station. Well, let's go do it! Okay, so here is the new temperature sensor. And in fact, we actually get one for free because this is designed to be used both indoors and outdoors. So there's a remote sensor. So the top row is the reading from the temperature and then the humidity in percentage below it on the left-hand side of the desiccator. And then the second line down is the temperature and humidity on the right, which actually gives us more information than we had before. Excellent. So now it's time, finally, after all this time, to use the desiccator for the first time. You'll see here I have two sample cups. The one on the left is to go in the near-infrared spectrometer, and the one on the right that I've piled quite generously is for the moon box, and it's for the X-ray diffraction machine on the desiccator sample. So without further ado, let's get them in and turn up the temperature. So I've selected the temperature at around 200 Celsius, and as you can see from the lights lighting up around the hot plate, it's heating up. Now is the time to put the samples on. So let's take a pair of tongs, like these ones. And first let's put in the one for the near infrared. Gotta do this quick, because remember, nitrogen atmosphere inside. Okay, that's the first one in there. Now, to get the larger one. Got to be careful, don't want to tip this one up. Okay, again, as quick as possible. Right, there we go. And it's alright because I can always increase the flow rate if I want to replenish the nitrogen in there, because it's going to be in there for about 3-4 days now. Okay, so the next thing to do will be to just basically check that the sensors are working by seeing whether the temperature and the temperature increases and the humidity drops. So let's leave it for a while and see what happens. Notice already that after only 5 minutes, they're already starting to change in colour around the outside edge as they heat up, as the water content within evaporates out into the box. The samples have been in for just over half an hour now, and as you can see, the temperature inside has risen from an initial 20 or so degrees to 38 degrees on the left-hand side and 42 degrees on the right-hand side. After about a day, the pressure on the nitrogen cylinder has lowered to about 60 atmospheres, or 60 bars. Now, we'll know that the cylinder is empty when it gets down to about 10 bars, so hopefully this one cylinder should last for the full 3 days to prepare the first sample in the desiccator. After running the desiccator for 1 day, the samples seem to really have changed colour, because remember it was effectively a brownish type colour right at the beginning, and now it's almost gone slightly green, which is certainly interesting. And also, if we notice the temperature inside the box, it seems to have stabilised at around 45 degrees, which means that the theoretical profile I calculated of how the temperature would change, you know, starting off a value, increasing and then levelling off, seems to have held true. Fantastic. Theoretical physics seems to actually work. Thanks for watching. Next time on Project PhoboCam, the project moves to its most vital phase, with our desiccated regolith subjected to an artificially reconstructed Phobos environment. The thermal infrared emission data from this experiment is the key piece to design our landing site selection camera for a sample return mission to the moons of Mars.